Jim. Turn off the waiting room, Jim. Good evening, everyone, and a very warm welcome to the Astronomical Society of Edinburgh's October in-person hybrid meeting. A bit more hybrid tonight due to the welcoming weather. I'm Neil Martin, President of the Society. I'd like to extend an especially warm welcome to our guest speaker for this evening, Dr. Richard Miles, who is joining us remotely. Continuing the warm welcome, our latest new member, Paul Buxton. Paul, I don't know if you're in the room or joining us remotely. If you're in the room, give us a physical wave. If you're on Zoom, give us a virtual wave. That brings our membership to 208. Let's all welcome Paul in the usual manner. And that's a timely reminder, if you're joining us on Zoom, please make sure your microphone is muted. So our topics for this evening are two comets like no other, presented by Dr. Richard Miles. I'll introduce Dr. Miles properly in a few moments. Then we have the Sky in October, presented by Alan Pickup. And we have a members presentation on double stars from Hugh Somerville. Now, I don't see Hugh in the audience. Oh, he's arrived. Cool. I was going to say that might mean you'd get an early finish or an extra cup of coffee, but now you've got to listen to Hugh's session. I'll finish up with a look ahead to the coming soon highlights before we serve up tea, coffee and biscuits in the room. If you're joining us on Zoom, then I'm afraid it's self-service. Approximate timings are on the screen. I'll try and keep us to this schedule, but I'll need your help to do that. So let me quickly conclude my introductions for the evening by summarising the resources available from our society, a collection of both public and members-only content. Our website has a members area which contains details of our project activities, and our members' communications include regular newsletter and a volcanically active WhatsApp community. On the subject of members groups, we also have a monthly imaging and observing group. This is held online and is for members only. And this group runs our Image of the Quarter and Image of the Year competitions. And this is our reigning Image of the Year, the Elephant's Trunk Nebula, which was created by Eros Tang. And I'm going to continue showing that every month until there's a new Image of the Year. So if you're not currently a member, but are interested in learning more about the projects, including our remote observatory in Spain, or discussing imaging and observing or creating prize-winning images, then these are the basic details you need. There are several benefits to becoming a member, and the cost is incredible value at £32, less than £3 a month. And if you qualify for the concessions rate, it's half that. For returning members, just a reminder that the fees for this year are now due for payment, and full details are available on our website at astronomyedinburgh.org/membership. So now it's time to focus on the main talk this evening. It's my great pleasure to formally introduce our guest speaker, Dr. Richard Miles. Now, Dr. Richard Miles is a retired research scientist, an ex-president of the British Astronomical Association, and long-time specialist on asteroids and comets. He remains a keen active observer, having had an observatory of sorts since the age of about 9. And 3 years ago, he moved to Cerne Abbas in Dorset, and now uses remote telescopes over the internet exclusively. He helps run projects involving amateur astronomers from around the world, and Mission 29P is the main project operating as part of the BAA's Comet section activities. It's been running since 2014, and this year's apparition attracted 45 observers using 62 telescopes. So, ladies and gentlemen, here and remote, please welcome Dr. Richard Miles.
Richard, if you could now start screen sharing, please.
Hold on. That's right. How's that? Is that going?
That's fine.
Ah, great. Okay. Well, thank you very much indeed for inviting me. I would normally be attending the BA's Comet section meeting, but this is the next best thing because that meeting's tomorrow, and this way I don't have to battle through the gales to get to Edinburgh. So I much appreciate that. Let's just say, first of all, that comets are absolutely fascinating objects, and they could, many people believe that they delivered molecules to the Earth when the Earth was cooling, and that the necessary chemistry for life was partly due to comets impacting the early Earth. Now, when I'm talking about two comets like no other, you can see two pictures of them there. But why are they like no other? These are the two in question. And basically, what's different is that each of these undergo what we call outbursts. And they outburst more frequently than any other comet we know of. Okay. So an outburst is when, within a very short space of time, the nucleus of a comet, something happens and it throws out a lot of new material into the vacuum of space, and that then expands and it produces an outburst coma. Now, professional astronomers have long studied comets, but one of the things that they've never really taken on board is the fact that there are four states of matter. One's plasma, and there's lots of that in space, but the other three are just simply solid, liquid, and gas. And most of the literature that's published about comets generally talks about the solid surface and gaseous products that come out. Well, comets that outburst in this way these two do, they're not the only ones. Around about 5% of all comets outburst such that they'll, at some point in their life, they'll suddenly get a factor of 10 brighter. And it's the same underlying phenomenon in all cases. But we are particularly interested in 29P, and as already heard, that project's been running for nearly 12 years. But what happened in 2023 is a comet called 12P Pons-Brooks turned up on our doorstep, and it started outbursting. And what was wonderful for us was that we'd been working on 29P for so long that people had almost come to just accept it as a one-off, as a bizarre object. And I think the professional community, to some extent, lost interest. But with 12P, it's a very different comet. And let's look at the orbits of these comets and look to see if they make any difference. What you're seeing here is a plan of the solar system, and Jupiter's orbit is in blue. And you can see orbiting just beyond Jupiter, orbiting the Sun, is Comet 29P. And the other thing that's noticeable is it's very circular. So we're all used to comets getting very close to the Sun and reaching perihelion, getting overheated, and they fragment and so on. But when these outbursting comets do their thing, they don't destroy themselves. Look on the picture here, and you'll see the orbit of Comet Holmes, which is a Jupiter family comet, or within the orbit of Jupiter. That underwent an outburst where it became 400,000 times brighter, created a new star in the constellation of Perseus, and yet it survived completely okay and continued its life and actually outbursting later. You can also see Halley's Comet, the orbit of Halley's Comet. And I'm showing that because, believe it or not, Halley as well is an outbursting comet. And what's particularly interesting, on the next slide, I'll compare the orbits of 12P, Halley, and 29P. Oh, sorry, just go. These are the orbital characteristics. And what I want to draw attention to is the fact that Pons-Brooks has an orbital period of 71 years, and we all know that Halley takes 76 years to get around the sun. And so these two comets are rather similar and quite the opposite of 29P, which is a very circular orbit. Its eccentricity is only 0.04, and yet it's been outbursting all these years, ever since it was discovered in 1927. I'll just go back. Pons-Brooks discovered his comet in 1812, and that 71-year orbital period meant that the next time it came around was in 1883, which was when William Brooks discovered it. And because the two of them basically determined the orbit without the second discovery, its orbit wasn't that clear. It became Comet Pons-Brooks. Now, George Alcott, 71 years later, after William Brooks, has done a drawing of 12P. And likewise, when he saw it, the comet underwent several outbursts, a few. Now, another famous comet observer is Caroline Herschel. And this is why I wanted to mention about Halley, because Halley's comet has been known in the past to undergo outbursts like 12P and 29P. These are drawings by Caroline in 1835 to 36. And those shapes are very, very characteristic of a very energetic outburst, where there's so much material thrown out, so much gas, that it expands in a spherical shell. And what you can see there are sort of two shells, one inside the other. Now, Caroline Herschel, you remember, helped William Herschel, her brother, to observe. But that was in the 1780s. This is 1835. She's 85 years old. She's observing, and she's observing Halley because she knew from her experience that what Halley was doing was something very special. And she's really the first person to recognize that outbursting comets need to be observed. So we have set up a project where we're concentrating on 29P, but if any other comet undergoes an outburst, we have two groups that are active. One is the group of amateurs that the BAA encourages to join. And we have about, for example, for 29P, we have a group with about 55 people, many of whom are the observers. And the other group is a group called Comet Chasers. Now, this is something that came about from what originally was called the Fawkes Telescope Project. And that became a network of telescopes around the world called Las Cumbres Observatory. And for some years now, various people from different countries, and particularly schools and colleges, have been contributing by taking images or even controlling a 2-meter telescope to grab images of these interesting objects. Right. Let's see what they look like. These are sort of moderate outbursts of Halley and 29P. Now, the thing about Halley is it went through perihelion in 1986, but this outburst happened 5 years later when it was 14 AU from the sun. And this is one of the characteristics. They can outburst even though the comets are very far from the sun in a cold environment. So 29P sits around about 6 AU from the sun. And the first time that 12P was discovered outbursting was in July 2023, when it was almost 4 AU from the sun. 12P's greatest, most intense outburst was in November the 14th. And I don't know if Nick James is in the audience, but Nick was he was actually observing this comet 12P minutes after it underwent this outburst, which is 1,000 times brighter than the one I showed you just before. So this one on the left, the outburst is only so slight that the comet is slightly brighter on one side. But when it's 1,000 times more intense, this is what happens. And you can see two shells. The inner shell is mainly the dust that's blown out. But much of the outer shell is gas that's traveling much faster, and so it expands that much more quickly. Now let's look at the observations that comet chasers did. This is a really good example of why amateurs can contribute. And if you can have access to your telescope, you can go out and observe within minutes of something being discovered, then following outbursting comets is a good pursuit. So an amateur called Cerne Abbas discovered 12P undergoing a 4 or 5 magnitude outburst on the 20th of July. And if you can see the outburst here, and the data points are just images taken with 1 meter and 2 meter telescopes on the Las Cumbres network. And you can see that within hours, some of the comet chaser observers managed to schedule observations, and we followed this comet very closely. Now, we were trying to do 2, possibly 3 things with this. What we were trying to look at is the nucleus. We were using larger telescopes, and in that way, we could get closer to the nucleus. And what we were looking for were variations in the brightness. Now, we had to wait for the outburst coma to expand and really escape from our field of view so that we could just study the nuclear region. And what I've highlighted there with the red arrows are 3 periods when the nucleus appeared to be quiescent. The first one, it's still fading as some of the dust from the outburst goes out of the field of view of the measurements. But by the time the second one arrived, we managed to get something like 11 nights observation, different days of it. And then there was a third opportunity. Now, what we can do with this is we can try to study the nucleus on its own without the coma. And how do we do that? Right. If you look in the inset in the top left, that plot, what we're showing there is the profile of the coma, the brightness of the coma, as you go from the nucleus itself, and you move outward, the extra amount of light means the magnitude of the comet looks brighter and brighter as you use a larger and larger aperture. But what you can do is you can measure the brightness in different size apertures, but then you can extrapolate back to a 0 radius, which is as though you're trying to measure just the nucleus without the coma. Well, that's all well and good, but in fact, you can't actually do that because we're suffering from atmospheric seeing. The seeing degrades the image. And so what we find is that when we extrapolate and we get the intercept, that value, the brightness at that point depends on what the seeing is like. So here we are on the main graph. You can see there are 3 colored sets of points for the 3 different periods when we were able to study the quiescent nucleus. And you can see the x-axis shows the seeing in arc seconds. So you see how strongly the brightness of just the extrapolated brightness of the nucleus changes as you go to a much clearer, steadier atmosphere. And what we can do is we can extrapolate, there's two things here. We can extrapolate that down to perfect seeing. So the FWHM is 0. And that shows that the nucleus, the diameter of the nucleus is somewhere between 15 kilometers and about 17 kilometers. Now, in the literature in 2020, professionals had published an upper limit of 34 kilometers. So you can see it's a lot smaller. Now, through this talk, I'm going to be wanting to compare 12p with 29p. So it's important to realize that 29p is actually 4 times the size of 12p. So that means it's, 64 times more massive on average. And that's part of why 29p is particularly interesting to observe. Now, the second thing I want to draw your attention to on this is the fact that these observations were done over many, many nights, right? And they come in 3 sets. So the blue points are when the quiescence was at its lowest and it was pretty flat. So that's the best sort of calibration. You'll see that the brightness is lower than the other 2. But what's really stands out, certainly for anyone interested in looking at light curves of asteroids, is that as a nucleus or an asteroid rotates, its brightness fluctuates. And if it's a sort of potato-shaped object, then it will fluctuate in a sort of periodic sense. And typically, it would be about a variation of 0.4 magnitudes. So that's usually cometary nuclei vary more than asteroids do. So quite often you might have a bilobal, to a very extended one, and then you could have a 0.7 magnitude change. Now, if we just look at the blue points and the line through them, can you see how close they are to the optimal best fit? They're only plus or minus 0.05 of a mag, varying from night to night to night. And that means this nucleus is incredibly spherical in shape. It's not, it's not a potato shape. It's more like a tomato. And so that has a bearing on how it behaves after it outbursts. The BAA Comet section later in the year in 2023 really got to grips with the comet, and many amateurs were able to follow it. And so, although we only saw 4 outbursts in the first 3 months, there were many other ones that followed suit. And from this, we're able to actually measure the intensities of that. So I'll just go back to that plot here. Remember I said it's about a 15-kilometer nucleus. Well, knowing the size of it and knowing the albedo, the reflectivity, we can calculate how bright the nucleus would be if there was no coma there. So for each of these data points here, we know how bright the nucleus on its own is. And if you know that, you then know how much brighter the outburst has changed the comet. And we express that in terms of what I call nucleus equivalence. We can express how bright an outburst is in how many times brighter than the nucleus on its own is. And that's a really great way of expressing it because it corrects for all the changes in distance and so on. And you're comparing like with like. So I mentioned and I showed you the video of the expanding eruption of Pons-Brooks, which was the November the 14th one. That was the most intense, and it was around about 1,500 times as bright as the nucleus on its own. So really, actually brighter than any we've seen from 29p. And Nick James, for some reason, he was observing it sort of minutes after it started. And this is great because we can use that to look at what was actually happening. And we've seen this several times in the case of 29p. And here, the next plot is work of Jean-François Soulier, who also observed an outburst, but he started observing it before it actually kicked off. And what I like to draw your attention to is how suddenly it starts. It doesn't sort of just gradually build up and get bigger and bigger like a jet in a typical comet, a long-lived jet. So what we can do is we can look at just the start of the outburst. And here we are. I've tried to plot the two comets side by side so that you can see what was happening. And that 30 minutes gives you an idea of how quickly things were changing. And what happens during the initial stage is you get a cloud of material that's opaque, and you get a lot of ice and gas, and that vaporizes in the vacuum of space, and the cloud is blown up just like a sort of blowing a balloon up, and it accelerates the dust, and then it spreads out to a larger size, and it starts to become translucent so that you can see through it. It's not completely opaque. Now, the two things here are very similar. This is a very similar behavior. And what it's characteristic of is a sudden release of material that only takes minutes for it to eject from the nucleus. So this is rather like a volcanic eruption on the Earth. And indeed, we think that this is a cryovolcanic eruption in a very cold region on a cometary nucleus. And instead of being red hot lava, what we've got is a very cold but still liquid material based on hydrocarbons or liquid nitrogen, liquid carbon monoxide. And what has to happen is it has to be held beneath a crust. Right. Now, I'll come back to talking about 12P, and let's look at all the different outbursts that 12P had. Then we'll look at 29P in a little bit of detail. We'll dive in some detail, but there's lots more I can't mention because there's not enough time. And finally, although I've been rather critical of my professional friends, they did manage to use the James Webb Space Telescope to observe 29P, which I'm eternally grateful for. And I'll show you some of the results. Some have been published and some that are yet to be published. Okay. So 12P, it had 16 outbursts that we detected. This is the long list. There were 14 before perihelion, 2 afterwards. And you can see on the right are the intensities. The one I've highlighted is the very first one. The next one I want to draw attention to are these two. Now, these two happened within less than 24 hours of each other, and both quite strong. And this is a characteristic we've seen recently for 29P, where one outburst seems to trigger a second one. Then we've got the most intense one. We've seen that. We've seen pictures of it expanding. And then finally it reached perihelion. So what I'll do later is I'll compare those intensities with what we see with 29P. Right. Another thing that we can look at here, which is rather surprising, is that we are able to detect these outbursts because we observe very frequently. So the groups of amateurs and the comet chasers are taking lots of images, and the professionals can't do that. And so if you look at the time of the outburst, you'll see there's a delta T, an uncertainty in the time that it actually took place. And often it's, better than 1/10 of a day. So we get a good fix on that. So we can start knowing the times between the outbursts. We can say, is there a periodicity? Is there something acting like a clock? That as the nucleus of the comet turns, a particular region is outbursting. Well, indeed, surprise, surprise, it does seem that way. Here's a list of, if you just look at down at the bottom, I've highlighted in the red the conclusion of looking at the times between the outbursts. And if we look for periodicity, there are 12 outbursts where we see either a one revolution or two revolutions, two times spin of the nucleus between each of the outbursts. And that's if we assume it's a 14.8 day rotation period. So sometimes it'll outburst after 15 days, plus or minus, and sometimes it will take 30 days. And that is, we see also in 29p. So this is really great because this shows that this is a really slow rotator. And that's something I haven't mentioned yet. The orbit of these comets isn't important at all. You know, Halley gets very close to the sun. 29p never gets anywhere near. It only varies by 0.3 AU, and it always stays beyond Jupiter. So the thing that's special is that they rotate very slowly. And we'll come on to this because for 29p, the rotation is even slower than this. And Comet Holmes, we think, had a rotation period of about 44 days. Normally, a comet will spin once about every 12 hours, maybe a day. So these are exceptional. And remember I said that 5% of comets seem to do this. 5% of comets will actually have this sort of very slow rotation rate. Right. You might have heard of the Devil Comet, because about a week after it first outburst, we took some 2-meter images, and the one on the left is what was posted onto the internet. And lo and behold, the press or whoever got to it. And when somebody said there were two horns, seemed to be two horns in the coma, then immediately the word devil was ascribed to this particular comet. But also somebody also sort of from Star Wars, that the Millennium Falcon spacecraft, fictional spacecraft, also seem to be rather similar to this 12p eruption. Well, you know, I'm saying that 29p is very similar in many respects. Well, it can do the same as well. Oops, sorry, I've just, I hope that's not on your screen. It looks as though it is. Right. So 29p also can generate that appearance. And the reason is it's to do with the nucleus blocking the expanding outburst coma. The nucleus of 29p is 4 times bigger than 12p. It's a real obstruction. So if the intensity of the outburst isn't great enough, it will create a shadow in the expanding material. Oh, can people see the a red line on the image?
Yes, your red line is on our screen too.
Oh, right. I didn't know that. I use my mouse to do that. I'll see if, yeah, I need to see if I can get rid of that. I'll just drop out. And now it's not moving. I've never seen that before. Uh, I'll see what a backspace does. And now. Anybody have any ideas what that's doing? It seemed to draw with the mouse for some reason. I don't think I'm going to be able to get rid of that somehow. I can't select it. It seems. There's a thing called annotate.
Control Z.
Oh yeah, Control Z might do it, but no. Raw. I'm looking for delete. Hold on. Yeah. Right. That's a new one on me. Okay. So what we got here is 6 different outbursts, where there was a really energetic one in the case of 12P. And you can see that the horns that were there in the first outburst are repeated in slightly different ways in the different ones, depending on the energetics of the strength of the outburst. So just very quickly, notice that they tend to be aligned in roughly the same direction, 218 degrees plus or minus 30. So the concept here is that the region on the nucleus, initially it's nighttime and it's behind the back of the nucleus. And as the nucleus turns, it's turning in a retrograde direction. So you could see on the bottom left, the yellow star is the site of the outburst, and it appears over the horizon, which is the sun rising. And as the heat of the sun builds up, it weakens the surface, and the pressure beneath induces a cryovolcanic eruption. Now, that eruption expands in like a spherical sense. And so if you imagine that you've got an almost spherical nucleus, what happens is it's a bit like the wing of an aeroplane. You get this Venturi effect where the dynamics of the flow are sufficient that it gets squeezed as it goes around all the different sides of the sphere, the edge around the different circumference of the sphere. And eventually what happens is there's not enough gas to keep accelerating any more of the dust. The dust acceleration stops. And so the imprint of the nucleus, the shadow of the nucleus, is fixed forevermore as it then expands. And all you then see is the same shape, and it just gets bigger and bigger as material moves out. And that's the hypothesis behind it. So the image in the bottom center there shows that the shadow of the nucleus is only about 10% of the size of the coma. And that means that the accelerating period meant that the coma became 10 times bigger on average than the nucleus before it had lost the ability to then imprint a fingerprint, imprint an impression on it, and thereafter it stayed the same. Whereas the very first eruption was less energetic. It was much further from the sun, so the gas wasn't traveling as quickly, which is also a factor. And so it produced a bigger shadow. And it's the sphericity of the nucleus that creates that uniformity of the horns. Right, now I'm going to move on to 29P, and I'll touch back base with 12P again briefly. But what I want to show is just a few things as illustration of some of the things we find. We've been observing to 12 years, and this image here is one that was taken a week after the most intense set of outbursts of 29P. There were 4 outbursts in the space of just over 2 days. And so this is the greatest example of a triggered outburst. And strangely enough, Charles Chamber was able to get the 8.4 meter Gemini telescope to image it, but they were frightened of burning out their detector, so they only used 1-second images. And this is a summation in 3 filters of 45 seconds of imaging. So that's what you can get with an 8.4 meter telescope. Think what the extremely large telescope will do in future. Right, let's look at 29P's record. There we go. Well, here's some results of observation by amateurs done in March, mainly in March of this year. So the beauty about encouraging lots of observers is that it allows you to do things you wouldn't do if you just try to observe it on your own. So what we're seeing here is we're seeing 5 separate outbursts, and you can see how they are very sudden. They take 30 to 60 minutes to really take off, and thereafter they just expand and then fade. And this is something that wasn't known before we started the project in 2014. We saw our first, what we call mini outbursts then. And these seem to be slightly different cryo eruptions than we get with these strong outbursts that are so impressive. And that's why they've gone undiscovered, undetected before 2014. So one of the hypotheses is that, like an eruption of a volcano on the Earth, there are 2 types. There's one that's called an effusive volcano, where it just spews out some pressure beneath the crust, and it just has an opening. And say on Hawaii or Iceland, they're prime examples, they just spew lava. And then the other, the explosive, is where they're held under pressure until a plug that blocks the volcano suddenly is blown out and the pressure released, and you get an explosive type of eruption. So these could be very similar to where the crust of the nucleus cracks or is open, but there hasn't been a buildup of what it is gas dissolved in the magma. So on the Earth, if you dissolve water in red hot basalt molten rock, it actually dissolves in quite high proportions if you've got a very high pressure holding it in. But then after that pressure is released, you get a really great eruption. Now, this is just 1 month of data, and you see the beauty that of being able to define what really was happening. Here's the full apparition that finished in July. And I've circled that data I was showing you just now, so you can see where these mini outbursts happen. Right. Now, on the bottom axis, I've got rotation number 1, 2, 3, and 4. We think that this nucleus of 29P takes virtually 58 days to spin once. And what you can sort of roughly see is you've got 4 groups of activity centered after each 58-day period. Now, we think it's 58 days because back in 2010 to 2014, we weren't running the project, but amateurs were still observing, and they reported their results to the Minor Planet Center. What we found for 4 years on the nucleus of 29P, only one side was erupting. Because it went on for nearly 4 years, we were able to get a periodicity out of it. Anyway, 2010, fast forward 1 orbit of the sun later, it's got an orbital period of 15 years, 2025. So 2025 is the start of the next 4-year period when we might expect to see this one-sided sets of eruptions from the nucleus of 29P. If we do, we've got three more years, really, 4 years, to complete an orbit of the sun. If we do, we'll be able to confirm the rotation period. Now, it's just as a comparison. I've got 10 more I like these I can show you, but none of them are the same. There's a seasonality. As the comet goes around the sun, it's in a circular orbit, but because it will be tilted, the spin of it is tilted, it will have seasons. So a northern hemisphere will have a winter, and then it will have a summer, and conversely, the southern hemisphere in reverse. I'll just pick one other set of observations, which was in 2020, 4 years before that. And I'm showing it on exactly the same sort of scale. I've squeezed and stretched the bottom one, so it really is identical to the top one in both directions. And you can see that they're qualitatively quite different. So in 2020, there was a long period of mini outbursts and very few strong outbursts, maybe only 3 really strong ones. Whereas recently we've had many more. And here on the far left, you can see where we had 4 outbursts in the space of 2 days, virtually. Very intense ones. Right. So that's a really good example of how, depending on where the comet, the nucleus is in its orbit around the sun, which side is facing it, the activity changes. So how many actual outbursts have we actually counted and measured? Well, it's 268, believe it or not, in about 11 years. If you plot them all on a log-log plot, you get something looking like this. Yeah, it doesn't tell you very much, but what I'd like to draw your attention is that the mini outbursts numbered 156, and we've got a definition here. That figure of 4 is the cutoff point. Weaker than that, it's a mini outburst. Stronger, it's a strong event. And if between each outburst there was the coma disappeared and then there was an outburst fresh, it would appear along the dashed black line. What happens is there's one outburst, and then before the chance for the coma to all dissipate, another one happens. And so because you're measuring the bottom, you're measuring the outburst amplitude in magnitudes, then the magnitudes are going to be lower. And so depending on that, you get a spread. It's not really that informative. It just sort of shows you the number to split. What's more interesting is to see what happens over time, over the 11 years or so we've watched them. So here we are. What we're showing here is, again, the intensity as a log plot on the left. But what we've got now is time, the 11 years. So the top there, you can see the year 2013 through to 2025. And you can see I've colored in red what I call strong and blue, weak, the mini outbursts. And see that you can see this difference. There's 2021 in the middle, and you can see how the weak outbursts are very separate to the strong ones. And yet in 2025, that was much less the case, and we had many more strong outbursts. Now, what would happen if I showed you the outbursts that I was talking about for 12p? It had 14 outbursts before its perihelion. So we can actually plot that on the same plot as this. And there we go. Obviously, it only spans about 9 months or so. But you can see how, because we were using large telescopes, 2 meters and 1 meter, we actually detected 3 mini outbursts, 3 faint ones, and many more strong ones. So here again is the similarity. One comet in a circular orbit, whereas the other comet is in highly elliptical, and just like Halley, it only comes around every 70 odd years. Right. What I'll show now is I'll just show you the strong outbursts, and then I'll show you the weak outbursts alongside. And what I'm plotting now is something else. I'm not plotting time on the x-axis. I'm plotting the time between an outburst and the previous outburst of that type. So how long was it before another outburst, strong outburst, happened? And this is the distribution. Now, the 58-day rotation period is over there on the right. Over on the left is a group on their own, which actually are the triggered outbursts, and they seem to be a separate class. So one of the hypotheses there is that when you get a really strong outburst, then a lot of material on 29p falls back, and it crashes into the crust and is likely to damage it and create a weakness, and then the pressure beneath blows through and you get a second outburst. Remember, we had 4 in quick succession early last year. Now, another thing is that if we're, say, plotting here the time between an outburst and the next one, if you've got an outburst because a site is facing the sun, what will happen to that site half a rotation period later? it will be on the other side in a very, very cold environment, subdued. And so the other side of the nucleus will have to come into view in the same position and then outburst from there. So, like I said, that we have had evidence that one side is more active than another. This gap in data just here tends to support that. Right, I'll now show the mini outbursts. And what I've plotted here is I've plotted them in linear intensity, because that way you can see why we have a gap. For these weak outbursts, they tend to be really weak, especially if it takes a bit of time before the next one appears. So the longer it takes before another effusive outburst happens, the less likely it's to happen. And so and certainly you don't get stronger ones. So that's again another just example of illustrating how there are two classes of sight on the nucleus. Right. Now, do we get to the James Webb Space Telescope? Yes, here we are. Fantastic. The most marvelous instrument, the most powerful telescope ever. For another 5 years, it's going to reign supreme before the extremely large telescope gets into operation. But they are very complementary, and James Webb is quite some instrument, and so pleased that it was able to be a successful deployment. It really was an astounding achievement, and that's because the instruments on board and the place it's observing from is so special. Now, I mentioned that it was used, I think it was February 2023, when it spent several hours imaging 29P. And 29P had an outburst 7 days earlier, but by the time Webb had managed to image it, because the field of view of the instrument is only just over 3 arc seconds, right? The outburst coma from that previous one had completely gone. And this was really good, actually. I didn't want it to observe an outburst. What it did, it observed it in the comet in the quiescent state. And remember I said about 12P, we wanted to observe 12P in quiescent, because to properly understand it, you don't want to be obscured by clouds of dust and debris blocking your view. And so James Webb saw it as a quiescent comet. Now, all comets emit gas and dust all the time. There's always an underlying continual level of activity, and the closer it is to the sun, the higher that level is. But all comets sort of within 10 AU of the sun will be, in 20 AU will be emitting. And so what they did is they imaged, and I'll show you just one of the results that was published in the only paper that's come out. And this was by a group led by Sarah Fudgy, or the paper was written by Sarah Fudgy, and is it Andy Mackay was the principal investigator? Is it? Anyway, what you're seeing here are pictures of the very inner part close to the nucleus. So the nucleus is the sort of inside that black spot in the middle, and the top pictures are for carbon dioxide. They can actually image in the infrared and just see light emitted by carbon dioxide. So they can measure the actual amount, count the number of molecules that are in different parts of the coma. And that's carbon dioxide. So the actual images are the ones on the left that have been processed. The ones on the right are a modeled version of them. And the one that's really interesting is carbon monoxide, because 29P basically emits 99% carbon monoxide. The CO2 is only 1% or less. And so what you can see is this quiescent nucleus was pushing out carbon monoxide in one direction. and they were able to measure how much gas that corresponded to. Well, after a year, the data that James Webb obtained becomes publicly available, and you can download it from a website. So that's what I did, of course, to do that. Now, I'll just explain what this is showing. This is like having a CCD camera with 30 pixels on one side and 30 on the other, right? But these pixels are only 0.1 arcseconds across, and because it's out in space, there's no such thing as seeing. It's perfect, like Hubble Space Telescope. So they're able to dissect the image and produce that map, right? Now, it's not just taking through a single filter. Effectively, it's taking it through something like 800 or 900 filters, because what the instrument does, it takes the flux coming from the comet, and it splits it up into its wavelength parts, and it divides it up into something like 900. It can divide it up into 900 different wavelength bands. So you can take each one and analyze each of those narrow wavelengths. And what they did here was to use a range of narrow wavelengths for the carbon monoxide emission and carbon dioxide emission. Now, they've only produced one paper so far, but I am hoping there will be another one, because I couldn't resist doing the analysis myself. And one of the things, you'll go to the next picture, one of the things that the Comet chasers did is, we knew that James Webb was going to be observing, so we observed it both before and after Webb's observations. And we found, for example, that there was a strong outburst about 30 hours after Webb had imaged it. We'll come back to that. So remember I said about 12P that what we like to do is we like to measure the profile of the coma, how bright it is, and to extrapolate it back to zero radius to find out what the bare nucleus is doing. Well, this is what I'm showing here. This is a typical frame from James Webb. There's the nucleus. And what you can do is you can take these measurements of the integrated light for different radiuses, and then you can extrapolate back to zero radius. Now, the beauty, as I said, is there's no atmospheric seeing, so there's no correction necessary for that. So the intercept on the y-axis is the light from the bare nucleus, essentially, or very close to it. And because you can do that, you can therefore separate out the rest of the light that's not got the nucleus, and you can subtract the bare nucleus off. And what I did was to take a 6,000 kilometer radius aperture and add up the amount of light in that coma. So we come up with two figures for each wavelength. We come up with a figure for the brightness of the nucleus and then the brightness of the coma on its own. So this is just showing it for 4 different wavelengths, how it changes. But it's the intercept and it's the amount of light in the coma in each wavelength band that's interesting. You can plot out 2 spectra. Essentially, you can plot out the spectrum of the nucleus as though there was no coma there, or you can plot out the coma as though there was no nucleus. And this is what you get. In red is the nucleus component. Right? Imagine there's no coma at all. You don't see any emission lines on the red plot. You only see absorption lines, which is what you'd expect if the separation in the analysis is right. But look what you get in green, which is just the coma. So I need to explain that the red line has been twisted, so that it superimposes on most of the green plot, so that we can compare like with like most accurately. I'm just going to draw your attention to one thing on this. By the way, as I say, I'm waiting for another paper to come out with a proper analysis of this. But I couldn't resist doing it. And the interesting thing is that the strongest absorption band is this one here in the middle. You see it in red, see how it drops down. Now let's zoom in on that. There it is on the right, but on the left I've tried to show what's going on. The coma emission is a whole mixture of things, carbon monoxide, methane, ethane, and that's coming off in that region. But what you got in the absorption is you've got a set of absorption bands due to carbon monoxide. Well, I'm actually showing you where the CO band would be of ice, CO ice. And I'm showing you where the CH4, the methane ice band is. Not all these different molecules have been measured in the laboratory. And the key thing here is that the temperature of the ice varies the wavelength that you see it. So do you notice that if you were to shift these arrows, you could shift them underneath the observed absorption band, which is a broad band. And that's because it's likely that if the ice is at 50 Kelvin, that would account for the offset. But the other thing is that the band is a complete it's like a total occultation, where the light has disappeared. And that's because it's likely to be a mixture of methane, ethane, propane, carbon monoxide. Carbon monoxide can be dissolved in a solution of methane in all proportions. So it forms a stable ice. So there we go. That's basically one thing I wanted to show you. One other thing I'd like to talk about with the James Webb is, and this is the last point really, is that I've said all along that pressure builds up beneath the crust. Does James Webb help us to understand that? So I mentioned that there was an outburst 30 hours afterwards that was quite strong. So one of the hypotheses is, we'll just go back to that picture, that on this bottom left, this carbon monoxide jet isn't quite a jet in the sense of the word. What it is, it's gas that's leaking out through the crust. So it's symptomatic of the crust, and it's showing that the crust is porous, more porous in one particular direction, or both, that the pressure beneath the crust in that area is at its highest compared to anywhere else on the nucleus. And so it's like a smoking gun, except this time the gun hasn't gone off because it goes off 30 hours later. But as the pressure builds, eventually it gave way. So what I did was I took the images from Webb and I looked to see if I could work out the ratio of the dust to the gas in the coma. So here we go. Bottom left picture is actually a picture of the carbon monoxide emissions. It's the equivalent of that one I was showing you before, where you had 30 by 30 and you could see the CO coming off in one direction. There it is, that's the detailed view. And that's a summation of several slices, all grouping the carbon monoxide. And what you can do, I can use the data that's published to work out how much gas is in at each pixel at different distances from the nucleus. But then what I can also do is I can take the wavelengths that are due to dust. So that's the sort of the R filter band, or the Sloan R filter band. And you can take the first 10 or so slices and that will give you, add them up, and you'll get another picture, which is the dust on its own. And you can do the same exercise with the dust. Okay. What the right-hand image is actually not just a picture of the emission from the dust. What I've done is I've divided the dust by the carbon monoxide image. I divided just the dust image alone by the carbon monoxide image. So this is what's called a gas a dust-to-gas ratio image. It's a ratio image. So it shows you what the relative amounts are. Now, comets in general, really dusty comets, have a dust-to-gas ratio of up to about 10. If you look in this dark region of the ratio map, that ratio there is 1,000 times less than that. And on the top right, I'm showing the actual numbers. What you're seeing is a dust-to-gas ratio of 0.01 or even less. And that's 10 times lower than has been seen even in very gassy comets before. So this is the evidence, this is the conclusion, that what we're seeing is that gas is escaping through a consolidated crust, but it's not entraining, it's not lifting loose dust as it goes. That's what happens in most comets. As the dust is sitting there, minding its own business, and then a jet of gas comes from the interior, it blows the dust up into space, and that forms a dust coma. And essentially, it's a different process here because you wouldn't achieve such a low amount of dust. There's just too much gas. And that's because the gas is being effectively filtered through a porous crust. And therefore, the crust is holding pressure. So there we are. We've got two sort of independent pieces of evidence. One is saying there was an outburst from this region a day later. So what we were seeing with Webb was this pressure building up and the gas trying to get out. And it was only getting out in one direction. And of course, the other is that there's, it's depleted in dust. And so it's not a standard surface of a standard comet. So there we go. Right, nearly finished now. I just come back to mission 29P. There are some web pages about it, and we actually do have a group, groups.io group that many people will know about. And the new apparition, the last one finished in July. It finishes because eventually the comet gets too close to the sun. 29P gets too close to the sun, and so you just can't see it. Well, in the last couple of days, I've had two observers. I've had Jean-Francois Soulier and I've had Matt Dawson observing from Italy, and they both found that it's fainter than about magnitude 15 or 16 at the moment. So the new season for observing has kicked off. But I do need to thank all the people who've contributed. And so the last slide is just the list of the observatories and the people who contributed in the last 12 months or so of observing 29P. So there we go. Great. It shows what can be done if we all work together. Thanks for listening.
Thank you, Richard.
I'll stop sharing, shall I?
Yep. That was a fascinating story of the two comets, weaving in sketches from Caroline Herschel almost 200 years ago, right up to the observations by James Webb Space Telescope. So fascinating story. We've got time for one question in the room. Alan, I don't know if you want to carry on setting up while we're doing the questions. So do we have a question in the room? Thanks, Douglas.
Thank you very much for the talk, Richard. Can you hear me okay?
Yes, fine.
I was particularly interested by the dissection into dust and gas from the JWST observations. That's fascinating. But my question goes back to the visual images which you showed of the horns of 12P. Now, when I see these, I usually think that this must be a projection of an axisymmetric structure. In other words, a kind of gap in the surrounding coma along a certain radius, an axisymmetric structure. And then I was surprised by the image you showed of a very narrow pair of horns. which was actually itself curved. And I couldn't see how this could be a projection of an axisymmetric structure. Do you understand the structure well?
Yeah, I think if we can work with the professionals, I think it can be modelled suitably. It's to do with the business of this gas expanding and accelerating the dust, because essentially that's what creates shape in the coma. Okay, so if you had a very tiny nucleus and a very large amount of material emitted, it would just be a spherically symmetrical shape with no inhomogeneity in it. But as the gas expands, the pressure that it puts on the dust gets less and less, because the pressure of the gas is dropping very quickly. It goes very quickly. And it goes through a region which is called the Knudsen region, where it's just about to accelerate, still accelerated. But if the gas pressure drops very much more, it then is unable to. The vacuum is too high, and there's not enough force to. And it's to do with how intense each outburst was before that reached that point in time. And it only takes about 20 minutes. You can easily model that if you imagine the gas comes out very quickly and then it just blows up like a balloon. And you can model it. So what you find is that because if you have a very spherical nucleus, it's able to create this shadow because the sort of hydrodynamics, while it's still accelerating, causes the material to sort of zoom past the circumference and be squashed essentially by the body of the nucleus. And that speeds up it not only speeds up the dust a little bit more, but it also concentrates it in a narrower annulus around the sphere. And think of that annulus, then it's like a pipe really. It's an annulus, a hollow annulus, and the hollow is created by the nucleus being nearly a sphere, and that then goes into space. So when we look at the Devil Comet and we see the two horns, we're looking down at this hollow cylinder of dust, and that's what it looks like. You see the edges, but if you look carefully, you'll see the structure across the middle as well. Because as it squeezes past the edge of the nucleus isn't a perfect billiard ball. It will fluctuate. Now, when you get a really strong outburst, that's when you get a much bigger, and it's accelerating it for a longer period. So if there's any sort of progression laterally in the material, the angle it will strike the nucleus will change slightly, and so that will curve the cylinder. The cylinder will become a curved cylinder, but because you expand a much bigger dust coma before it's frozen in, the curved cylinder is a much smaller width of the entire coma, and then it stays like that for a week or two later as it expands, and that's all built in the first 30 minutes or so. So that's the basis behind that. Yeah. And without 12p, we wouldn't know that so clearly. Yeah.
Thank you again, Richard. Let's thank Richard for his talk this evening.
Yeah, it has been recorded, hasn't it? The video, because what I'd like to do is to share it with the people who are in the group who observe 29p. So I look forward to it becoming available on the internet. Okay.
Great stuff. Thanks again, Richard. And now it's over to Alan Pickup to give us some advice on what to look for in the sky in October. Alan.
Right, okay, now we've got it. Right, hello folks. Well, since we've been hearing about comets and we're hosting the BAA Comet and Meteor meeting tomorrow, I thought I'd start with an image some of you may have noticed in our society newsletter this week. This is of Comet 2025 A6 Lemon, and this is an image obtained by our ARCRO Merrill Observatory in Spain and processed by Robert Arnold. This comet is visible all night at the present time, on the verge of naked eye visibility, and it's a nice imaging target, probably becoming a naked eye object later this month. At the moment, it's best placed before dawn in the northeast, and later in the month, it'll be best in the west. But I usually start with the sun, so here we are. Let's deal with the sun. The sun's now heading further south of the equator from Virgo into Libra. So we've long lost our night-long twilight, and the nights are getting longer. And nautical darkness increases from around 10 hours on the 1st of October to 12 hours by the month's end. If you demand astronomical darkness, then you've got about 2 hours less than these times. We also have the end of British summertime coming up on the 26th of October when we set our clocks back 1 hour to GMT. I'll just say a bit about solar activity. Solar activity remains high, but I've seen indications that we are now perhaps a year past solar maximum. So we can expect the number of sunspots to decline now, but we should still be alert for aurora, and there have been several recently. For the moon, here are the lunar phases for October. Since it's the full moon closest to the autumnal equinox, the one on the 7th is called officially the harvest moon, despite what some websites will tell you. The autumnal equinox was, of course, on September the 22nd. That makes the following, and I'll just click that and label it as harvest moon. That makes the following full moon on November the 5th the hunter's moon, although tradition has it that the full moon in November is also called the beaver moon. Some of us caught the tail end of the total lunar eclipse on September the 7th. This is an image obtained by Horst from Germany, further east in Germany, of that total lunar eclipse. Here we see my usual picture of the entire 360 degrees of the equatorial sky stretched across the screen, with the sun's apparent path during the year represented by this wavy line we call the ecliptic. The sun itself lies here in the middle of that blue area, which represents daylight. The arrow shows the sun's progress during the year, progress southwards and eastwards. The planets all lie close to the ecliptic, and they're represented here by those purple splodges along the ecliptic. A couple of the planets, Mercury and Mars, we won't see in October, both set too soon after the sun and are hidden in our evening twilight. Mars, in fact, is only 4 degrees high in the west-southwest at sunset today, and it sets within the hour. Saturn, though, is very well placed on the opposite side of the sky. It was at opposition on September the 21st. And Jupiter, meanwhile, is a conspicuous morning object. You can also see it in the late evening, rising in the late evening. It's in Gemini, not far from Castor and Pollux in Gemini, and it doesn't reach opposition until early next year. And Venus, the third brilliant bright planet, is closer to the sun in the sky, quite low down in the east before dawn. Of the two most distant planets, Neptune lies quite close to Saturn, I'll come back to that later, and Uranus is very near the Pleiades. And here's the view looking north at mid-month at 10 p.m. Now, if you look in the top left corner, you'll see times when this star map is also appropriate. So the stars are in the same position as this at 8 p.m. GMT at the end of the month, 20 hours GMT at the end of the month. we can see the plough coming down towards the north, below the star Polaris. And as it does that, then Cassiopeia, higher up, climbs to the zenith, the two opposing each other across the pole star. And low down in the northeast, there is Gemini, and it's in Gemini, but not yet risen, that we find the bright planet Jupiter. It rises about 45 minutes after these times. But I want to focus on a different area, this one, which takes in the plough, and the reason for that becomes apparent when I click on it. There we go, because it shows the path of 2025 A6 Lemon, the comet that I've mentioned before, with its position indicated every 5 days and labelled every 10 days. It's named after the Mount Lemmon survey, which discovered it on January the 3rd this year on its way in towards the Sun. Perihelion is on November the 8th at 79 million kilometres from the Sun, and it'll be closest to the Earth on October the 21st at 89 million kilometres. It's in an highly eccentric orbit. The previous time it came to the Sun's vicinity was thought to have been 1,350 years ago, and it'll be next coming back in another 1,155 years. So this orbit means its orbital period drops a little bit. The magnitude is currently around 6, but it may brighten to magnitude 3 or 4 by the month's end. And by then it'll be about 20 degrees high in the west-southwest at the end of nautical twilight in the evening, with its tail pointing up and to the left. And it sets, by then it sets around 20 hours GMT. Whether the tail will be easily seen, I don't know, but I heard a report today that in some photographs the tail is showing up as 12 degrees long, so it's certainly sprouting a nice decent tail. And here's an animation obtained by someone called Chuck Ayoub of the comet and its tail showing its motion over a period of 69 minutes. And you can see features in that tail, this ionized gas tail streaming away from the Sun, features in there moving even during that 69 minutes, their motion being governed by interaction with the solar wind. Back to our view looking north in the late evening, I want to zero in on this area, almost directly overhead. Here it is. It includes the constellations of Cephus and Cassiopeia, the mythical king and queen of Ethiopia, who were also the parents of Andromeda. One object here is the star Mu Cephei, which was also called the Garnet Star by Sir William Herschel, and the name stuck. It's around magnitude 4, so a naked eye object, and binoculars show it a pronounced red color. Its surface is at 3,750 degrees K, almost exactly 2,000 degrees K cooler than that of the Sun. It's also very big, 1,000 times the diameter of the Sun, so if they swapped places, then it would even engulf the orbit of Jupiter. It's said to be the largest star we can see with the naked eye. Another interesting object, more for astrophotographers, is the Bubble Nebula. That's here. And here's a picture, an image obtained by Eros Tang of this parish. There are lots of illuminated gas and dust. Most prominent is the Lobster Claw Nebula. For obvious reasons, it looks a bit like a lobster's claw. And that's a major site of the formation of massive stars. Above and to its right is the Bubble Nebula. And this is an H2 region, ionized hydrogen region, around a massive star. And I can blow up the image to show you a close-up of the bubble itself. The stellar wind from the large star is driving out this, excavating this bubble in the nebula. Towards the lower right of the main image is the Northern Lagoon Nebula, which is similar to the bubble with an even more massive young star at its heart. And there are a couple of star clusters around, the Salt and Pepper cluster towards the top and the Dormouse cluster towards the bottom. Now let's look towards the west. The plough is on our right now because the plough's in the north. So the plough's over here, and the summer triangle is here, high in the west to southwest. I'll come back to the summer triangle later on, but I do want to mention Corona Borealis, the northern crown, which is sinking lower in our western sky. So it's still observable, and we're mostly interested in looking at the eruptive nova T Corona Borealis, which we've been following astutely with our ASERO facility. And this is a map from the AAVSO, the American Association of Variable Star Observers, for the brightness of T Corbo over the course of this year. And you can see that since mid-August, there's been a relatively sharp fade by almost half a magnitude, a fairly steady and relatively sharp fade. As you may know, as I've said, we're following this quite closely with our Spanish facility, but we will lose it when it drops too low in the west at nightfall. Let's turn southwards. Here we have Saturn as the brightest object in the lower left side of this plot. The only naked eye planet in the sky at this time of the evening. It lies south of the square of Pegasus, which is just approaching the meridian. And the planet has just crossed from Pisces into Aquarius. As it's moving westwards, it's retrograding through the period of opposition when it directly opposite the Sun on September the 21st. So we can look for Saturn near the Moon on Sunday night. And here are details for October the 16th, middle of the month. The magnitude of Saturn is magnitude 0.8. The diameter of its disk is 19 arc seconds. It's noticeably flattened. It's polar flattened because of its rapid rotation. The rings are 43 arc seconds across, but less than an arc second thick. The tilt is only 1 degree. And because Saturn's nearly edge-on, its equator is nearly edge-on, Titan, the main moon of Saturn, can be seen sometimes passing in front of the disk, perhaps accompanied by its shadow, and sometimes passing beyond the disk. Titan orbits Saturn almost exactly over the Saturn's equator. Titan, followed by its shadow, cross Saturn's disk next Monday morning, the 6th. By then, though, Saturn is close to the Moon, and they're sinking quite low down in our southwestern sky, not the best ideal conditions. There's another transit by Titan 2 weeks later in the late evening and morning of the 21st to 22nd. So that is one opportunity we have of seeing Titan in front of Saturn, and Titan passes behind Saturn in occultations on the evening of the 13th and again on the 29th. What we're looking at Saturn, I'll concentrate on this area. We'll zoom into this area, and here it is. As well as being south of the square of Pegasus, Saturn is also 9 degrees south of this asterism, the circlet of Pisces, which represents one of a pair of fishes in the constellation of Pisces. Closer to Saturn, to its north and its east, is Neptune, the furthest planet. And here are the details for Neptune: magnitude 7.8, just accessible through binoculars. Diameter 2.3 arc seconds, extremely hard to observe as a disk, but 2.3 arc seconds across, and it's 4,334 million kilometers away on the 16th. Returning to our wider view to the south, let's pick up on a few of the deep sky objects of interest. Almost in the center of this image, quite close to the star Enif, which marks the nose of Pegasus, is the 6th magnitude globular cluster M15. And Mark has obtained this image of this globular M15. This is sometimes called the Great Pegasus Cluster. It's one of the oldest known globular clusters. It's about 12.5 billion years old. It's 25,700 light years away, and it holds around 100,000 stars. Now, the square of Pegasus, as we know, can be used as a starting point for finding a couple of other interesting objects, deep sky objects, of which the most prominent is the famous Andromeda Galaxy M31. Take a line along the top of the square and extend it to the star Merak in in Andromeda, then make a right and you'll soon reach the oval glow of the Andromeda Galaxy. But on the other side of Merak, about the same distance, is the Pinwheel Galaxy M33. These two galaxies are members of our local group of galaxies, of which our Milky Way is a member. In a dark sky and in a totally dark meeting room, not too bad here now, we can be able to trace the Milky Way climbing up to overhead from the southwest. In fact, it's following this line here. And as it does so, it passes through the Summer Triangle, which is here, bordered or cornered by the stars Deneb in Cygnus, Vega in Lyra, and Altair in Aquila. So let's focus on that. Here's a close-up of that area. The cross, the northern cross Cygnus, is at the top of the diagram. Lyra with Vega, the upper right, and Altair towards the bottom. And there are several smaller constellations. Delphinus, the dolphin leaping out of the Milky Way in the lower left, and Vulpecula and Sagitta, the wolf and the arrow, actually within the borders of the Summer Triangle. Now let's look at some things in the Summer Triangle of interest. One in Hugh's benefit is Albario, the swan's beak at the end of its long neck. This lies at 420 light years away, and it shines at magnitude 3.1. It's a famous double star, which appears as single to the naked eye, but two stars through a small telescope. This is a picture taken recently by Ramsay McIver of the Society. There's two stars, one's an orange one, and it has a fainter blue-green companion, 35 arc seconds away. Also of interest is the Veil Nebula, over here in Cygnus. Large loop of heated and ionized gas that's debris from a supernova that occurred more than 10,000 years ago. Exposures over many years show its debris is still expanding, but it really only shows up well in photographs. Great photographic target, and lots of lots of astrophotographers in the group are imaging that. Something more easy to spot is the Cotanger, which is down here, also called Brocchi's cluster in the constellation of Vulpecula. It's 1.3 degrees wide and 1/3 of the way on the line between Altair and Vega, so it's very easy to spot. It's not really a cluster. The stars are just a chance alignment. They're of about magnitude 5 to 7, so you really need binoculars to see them. But they're also always easy to spot on images of the Summer Triangle. Photographs of the Summer Triangle nearly always find the Cotanger in them. Closer to the center of the triangle is M27, the Dumbbell Nebula, material ejected from a star, a sun-like star at the end of its life, as it evolves into a white dwarf. This is magnitude 5.7, a smudge quite easily seen through binoculars, but a nice photographic target. It measures about 8 by 5 arc minutes, and it's around 10,000 years old. We called it a planetary nebula because the first observers of it and similar objects thought they looked a bit like planets. The Ring Nebula in Lyra, M57, is another planetary nebula, much fainter though, magnitude 8.8, and it's only 1.5 arc minutes wide. It lies 2,600 light years away, and is another favorite for astrophotographers, though I say it's much smaller and fainter than Dumbbell. Enough of the south, let's head east. The brightest object in the eastern sky is Capella in Auriga, climbing up the sky during the course of the night. Taurus and the Pleiades lie to the south of Auriga, and Perseus sits above Taurus, and higher still we have Cassiopeia, as we've seen, higher still and almost overhead. I want to zoom into this region of interest, and that includes Cassiopeia. Here it is. Between Cassiopeia and Perseus, below Cassiopeia, is the double cluster of stars here, H and Chi Persei. Neil took this image of H and Chi Persei, a twin cluster, two star clusters that lie around 7,500 light years away. To their left, and at the same distance, is a pair of gaseous nebulae, the Heart and Soul nebulae, favorite photography targets together or as individuals. Here's an image by Ian Smith. The more northerly one, the Heart, lies around 3 degrees above the Soul nebula. Both contain clusters of young stars, which have created caverns in the cloud of gas and dust. And it's possible that these nebulae will lead to another double star cluster in a few million years' time, though the border between Perseus and Cassiopeia actually lies between them. So these are in Cassiopeia, so they might become, if we're still around in a million years' time, the Cassiopeia double cluster. Looking east again, I want to mention a third planet in the sky at this time. And this, I want to mention the second one that's in the sky at this time. We haven't mentioned Jupiter yet. And this one is in this. This one is near to Saturn. This one is near to. Well, it is the third planet because I've already mentioned Saturn and Neptune. This is Uranus, and this one is near to the Pleiades in the sky in this area, and that's a zoomed-in area with the path of Uranus from the beginning of October to the 10th of November. It's heading like Jupiter, like Saturn is. It's heading westwards. It's retrograding below the Pleiades as it approaches opposition on November the 21st. And the Radim Stano obtained this image of Uranus recently on September the 20th, the blue-green disk of the planet Uranus, and there's some details for it for the middle of the month when it'd be magnitude 5.6, just visible to the naked eye, 3.7 arcseconds across, and 2.7 billion kilometers away. Yeah, 2.7 billion kilometers away. Still facing to the east, but are winding on the clock by 3 hours to 1 o'clock BST. By then, the Pleiades are around 45 degrees high in the southeast, and Orion is visible, clear of the horizon below them. Capella has lost its status as the brightest object to the planet Jupiter, which is conspicuous lower down in the east-northeast below Castor and Pollux. Here is a sky even later. In fact, this is shortly before dawn, in fact, when nautical twilight begins at 6:26 BST on the 15th. On the 16th. By this time, Jupiter is 55 degrees high in the south-southeast, getting close to the meridian, but that is now outshone by the brilliant planet Venus, which rises in the east 2 hours before the sun. And you can see it low down in the east in this plot. Details for these two planets, well, there's the details for Jupiter, 39 arcseconds wide, magnitude minus 2.2, while Venus is more than a magnitude brighter, but only 10.7 arcseconds across. It is winding around the far side of its orbit towards the far side of the sun, a 94% gibbous disk. Now, the moon is also in this picture. You'll see it in the plot as being above Regulus, 6 degrees, in fact, above Regulus and alongside the sickle of Leo. And we'll see the moon to the left of Jupiter on the morning of the 14th, and it'll be strongly Earth-lit when it lies above right of Venus before dawn on the 19th. Now, the main meteor shower of the month is the Orionid shower, whose meteors diverge from this point between constellations of Gemini and Orion. This is a view looking south at 6 o'clock on the morning of October the 20th. By then, Orion is already crossed the meridian. It's now moving towards into the western half of the sky. And our brightest nighttime star, Sirius, is as high as it gets, which for Edinburgh is 17 degrees in the south. And Jupiter is riding high as it approaches the meridian. Meteors, of course, are seen in all parts of the sky, not just at the radiant. They stream away from the radiant, they diverge from the radiant, which is why it's called a radiant, and they're visible in all parts of the sky. So you don't need to be looking south or towards the radiant to see them. Details for the shower as provided by the BA handbook. Meteors from the shower actually have already started to be seen October the 2nd, and they last for more than a month. The peak, though, is on that night of the 20th or 21st of October, when the hourly rate for those with the moonless sky and the radiant high in the sky is around 20 or more meteors per hour. Those meteors are fast, and many of them leave ionized trains in their wake. And their parent is a Comet Halley, which we've already mentioned. And with the moon out of the way, conditions this year to observe it are held to be favourable. Mentioning Halley is a cue for another image of Comet Lemon. This one obtained a week ago by Dan Bartlett in California, showing its very nice, showing this time in colour, a very nice iron tail streaming away from, well, for a comet called Lemon, it's more like a lime of a head, but that's going to be the main interest over the coming month, I think. And that is all I've got for you this time.
Thank you, Alan. Fascinating as always. Thanks for featuring my image. I feel honoured. If only I can get to grips with my newfound presidential powers to do something about the clouds, maybe we've got a chance of seeing some of the stuff that Alan's pointed out. Thank you. Hugh, do you want to come up and set up? And what we'll do in the interest of time is I will just quickly tell you what we've got coming up in October. And then whilst we're having coffee, I'll run the slides on the screen so you can see what's coming up over the next couple of months. So tomorrow is a big day because we're back here hosting the joint BAA Comet and Meteor section meeting. Incredible collection of speakers, including Douglas. More details on the website. Hopefully, there may still be tickets left, Nick?
Yeah, there's space, so if people want to come tomorrow and they haven't booked, then I think it's
£5 and a fascinating day ahead. Online meeting in the middle of this month on Friday the 17th is The Secrets of Gravity, Professor Claudia Duram. And next Wednesday we have our Imaging and Observing group meeting for October. So that's what we've got in October. I'll put the slides up so you can see what happens in November and December. But for now, it's over to Hugh. Tell us about...
Can I take the bumper off?
Yeah, sure. Stars.
Yeah. I'll keep it brief and I won't... Are we on? No.
That's it.
Hello.
If you can aim to finish by 9:25 for coffee.
Oh, easily. So, some of you know that I've been taking images of double stars over the last 3 or 4 years. I'll explain a little bit. I'm not going to go into big technical detail. I don't do technical. Most of you know that already. It keeps it easier. So, how it started was I was taking images of the Orion Nebula, and I noticed there was a little patch of stars called the Sigma cluster. And then I noticed a reference to it, STF 761. And I didn't know anything about that. So I looked it up and discovered it was a guy called Frederick Struve, who was one of the original astronomers, same sort of vintage as William Herschel. I then carried on making lists. Found out a lot more about the Struves. There are about 5 generations of them, of which there was one, no, don't go into that. Yeah, the last one ended up in America in the 60s. So the 3 main categories of double stars either physical, uncertain, or not physical. I'll go into a little bit of detail on that later. And I started just randomly looking around to see if I could find other targets, just from previous shots, etc. Oops. So I'd created lists from Wiki and various other sources, and then I sort of used the constellations of Corvus and Equuleus as the basis of my charts. Two of the smallest constellations per square area, according to the IAU boundaries. So with graph paper, I started to plot each historical double star, and I used data from Stella Doppie and Simbad, both very good websites with lots of information, and also a lot of graphics. I was using Simbad the other day recently, because a couple of weeks ago, when I last used my 8-inch Skywatcher, I'd identified another double star in Equuleus, and I'd been trying for 2 or 3 others, and I was able to work out that I'd missed the other 2 or 3 by about 10 arc minutes. So I wasn't too far out, but there'll be another time. I've probably missed the best of Equuleus now at this time of year. So yeah, I've been happy to get any sort of image, and I was able to annotate the primary stars. I started creating my own catalogue. I've now got about 380, I think, altogether. And for me, it was important to show the difference between the ones that you can obviously see clearly and some of the rubbish images, which I'll need to try again. Now, it was important for me to make up a data sheet for each set of double stars. It's just something I did. I think it's one of these things where you're actually able to confirm the details for yourself and for other people. So using the ideas of the Hipparchus, the Henry Draper, Tycho, and BD, I can never remember his name, and some other references. So the various astronomers that I've looked at from historical backgrounds, Frederick Struve, Otto Struve, so that was his son, or possibly grandson, William Herschel, John Herschel, Sherman Burnham, South, and Joghier. So examples that I think most people know of, Alan mentioned one earlier on, Alberio. Alcor and Mizar is a great one for getting kids started with, because you can see it naked eye. But what they don't realise is that there's actually 6 stars up there, although I've never seen 6, I've only seen 3 of them so far. The Epsilon double, it's an easy target as well. My imaging, I use an Astro camera, and with the 8-inch, I can get down to about, I can split the Epsilon double down to about 2.2 arc seconds. Right. And we'll skip. Yeah, so the basic criteria was anything before 1918. So the techniques I've used, basically I take a very short AVI file, video file. One of the reasons that I've gone for these double stars is, for me, it's an easy target, because with the setup I've got with the 8-inch, unfortunately it's got a couple of mechanical issues which I still need to resolve, and so I can't take long duration imaging at the moment. So just a few seconds to get a double star, I'm quite happy with. Now, that's fine. So once I've got these AVI files, using PIP, an app I downloaded, you can convert them to TIFFs and just select the best frames. Usually, in fact, the shots that I took the other day, just a 30-second run. And from that, I just select one or two images, sometimes just one. And if it's got the target, I'm happy with that. So I use generally Registacks, and I compare the details with Stella Doppie, because that has imaging on it and it has charts, giving the details, the locations of each of the primary stars. Occasionally I'll use Deep Sky Stacker if it's a very faint image, but I don't use that so much now. And then I put it onto a PowerPoint, save the JPEG files, and upload it to my own Flickr pages. So I've got various catalogues that I've created. I haven't brought any with me, you'll be glad to know. Partly they were going to get soaking wet tonight. Right, and I just keep creating that database. Now, let's do that one. Yeah, so there are different types of binary stars, or double stars. Some of them are just optical. So two stars that appear to be close, but are not necessarily. If they're true binaries, then they're going to be one of them, or either of them, both of them, may be orbiting each other. And there's various classifications for these. There's also something that some of the people in the club do already with spectroscopic binaries. Eclipsing binaries, you may be able to pick up if you've got a good setup. The James Gregory up at St Andrews, they do exoplanet studies, and I'm sure they pick up double stars at the same time. Well worth going up there. We've been up a couple of times. Now, here's a quick... Yeah, Alcor, Mizar, and most people know that Mizar is split into two, but if you look closely, you can see that each of those is a double as well. But I think they're spectroscopic. That's the first time I got the Epsilon double, and then that's a slightly better. In fact, the first one was with the 5-inch Celestron. That's with the 8-inch Skywatcher. And there's Alberio, not as good a shot as the one Alan showed. Some double stars doing some funny things. So different orbits they have. I won't show that for too long because it might screw up people's eyes or whatever. So, next thing. There's a spreadsheet here that I've created showing the quality, all the details that I've picked up from Stella Doppie and Simbad. And I haven't updated it for months now, so it's need to do some work on it. Seem to be preoccupied with other things, and that's another version of it. I won't bother with that. What I will do just before I show some of my own images is on here is the constellation of Herculeus, and the green asterisks are the ones that I've already imaged. That's needing updated because I'm now up to about 38 out of, I think it's about 60 in that constellation. So I think this will be my last shot. Yeah. So I think it was Tim that asked me what my favourite double star was. This one here, STF 761 in the Sigma cluster in Orion. And each time I go back to it and have another look, you find that actually there's about 5 or 6 different combinations from different astronomers over the years. So it's just taking different shots and identifying, in the description up in the top left on this one, it's also giving the separations. For me, the separations are important because I'm trying to show a visual separation in an image. It doesn't really make much sense to do a double star without a separation, but I do anyway. I'll leave that running as if I can, yeah. slideshow. Yeah, there we go. If there's any questions, I don't know about anyone else, but you can ask me at coffee or partly because the seats aren't the best in the world for comfort. Thank you very much.
Excellent, thank you, Hugh. And
Wait a second, there were two other things. Just as a last thing, I'll leave it out. I forgot to show off the meteorite I have up at the observatory on Saturday and Sunday, so it's there for anyone to have a look at. That was given to me as a present from a very good couple. And it's there we go. Yeah, it's all the NASA missions patches. There we go.
thanks very much, Hugh. I was going to say there are times when seeing double is a good thing, and Hugh's just shown that, but he's kind of usurped that joke with the extra stuff. Right, tea and coffee is now served. That brings us to the end of the presentations for this evening. As I said, I'll pop up a rolling slide in a second as to what's happening over the next couple of months. Thanks for coming along this evening. For those of you on Zoom, you're free to go and choose a beverage of your own choice. Tea, coffee, biscuits at the back. Thanks, everyone.